In this video, I'm going to talk about surreal numbers, an extension of the real numbers. But I'm going to clarify first that although they are an extension of the reals, they're not a set, they're a class. But still, I'm not going to go too deep into that. So let's see, what are the surreal numbers? This is I'm going to use so that it's more similar to what we're used to. But they're not usually denoted like this. They're usually denoted with an N and a 0. So usually we learn all about the real numbers and how they include algebraic numbers, rationals, the integers, and natural numbers. And sometimes we used to learn that the reals are included in a larger set that we call the complex numbers. Right? So first we learn these, and these, and so on. And well, there's another way to extend the reals, which is not nearly as well known, but is still really cool. And well, this is what John Conway, the Game of Life guy, discovered in the 70s. And although we don't know many places to apply these numbers, well, we also didn't know where to apply number theory when people first studied it. Now number theory is applied in many parts of cryptography, security, and much more. But before we start, like often when we're studying surreal numbers, people are told to forget everything they know about numbers. We're going to start from scratch and create a system even greater than the real numbers. Still, I'm going to skip over some parts of this. So, the construction. The way John Conway describes surreal numbers is as follows. Any surreal number is constructed by two sets, L on the left and R on the right, where both can have any number of elements, including 0, as long as no element of L is greater than or equal to any element of R. We'll see later that this means every element of R is greater than every element of L. But for now we don't know what that means. To denote the form of a surreal number, we'll write it this way. Between brackets, like I said, and with this weird sort of slash. But we've forgotten everything, so we've forgotten what it means to be greater than or equal to. So we'll have to start with something that doesn't require us to use that part of the definition. Now, if you see here, no element of L is greater than or equal to any element of R. So we can't use anything with elements because that will require us using that part of the definition, which we can't. So we'll start with only the empty set, right? So that we have no elements. So our first number is going to have L equal to the empty set and R equal to the empty set. No element of L is greater than or equal to. We don't know what that means, but there's no element, so no element is anything. No element of L is greater than or equal to any element of R, so our condition is fulfilled. This means this is our first real number, but we'll just call it 0 for now. In fact, it is called 0. So now we have two elements we can use as L and R, which are 0 and the empty set. But this was we can call our first generation of our first day. Usually people talk about birthdays. So the first birthday of this one would be 0, and the next ones would have birthday 1, and so on. But I'm just gonna call them generations. For the next generation of surreal numbers, we've got 4 possibilities, right? 2 squared. One is this, but we've already used it and we called it 0. The other 3 are 0 as L and the empty set as right, left, right. Where 0 is this business here, and then the other way around, 0 as R and the empty set as L, and the other one is 0 and 0. But we still don't know if all or in fact any of these as real numbers. And to see, we have to check which ones satisfy our condition. For the first two, which either have L as the empty set or R as the empty set, the condition is satisfied. There's no elements to be greater than or equal to. However, for the last one, we have to see if 0 is greater than or equal to 0. And if it is, the form isn't a number. For this, we have to look at a second definition, greater than or equal to. As a real number, x is less than or equal to as a real number y if and only if y is less than or equal to no member of x's left set, no member of y's right set is less than or equal to x. That's a lot. But we just have to substitute everything there. This is defining less than or equal to in terms of less than or equal to, which seems circular, and it is, but we just have to substitute the stuff in there until we have all empty sets we can work with. So is 0 less than or equal to 0? These are real numbers. Well, we just have to substitute 0 in everywhere because both numbers are 0. So is it true that 0 is less than or equal to no member of 0's left set, which is the empty set, and no member of 0's right set, i.e. the empty set, is less than or equal to 0? Well, 0 was the empty set, and then the empty set as R. And 0 is less than or equal to no elements of the empty set, because, well, the empty set has no elements. The other condition is similarly proved. No member of the empty set is less than or equal to 0 because there's no elements. Then 0 is less than or equal to 0. Contrary to might seem from this, though, 0 bar 0, I'm gonna call it a bar, it's not a surreal number because, very loosely speaking, changing its 0's position will prove that the 0 on the right is less than or equal to the 0 on the left. And that proves a member of R is less than or equal to a member of L. Right? This one is less than or equal to this one. So if 0 is less than or equal to 0, the form is actually not a real number. But we saw that these two are. So far we have three surreal numbers. We call this one 0. This one we're going to call 1, and this one we're going to call -1. We'll see later why this is true. Then I'm going to skip over some stuff. We have been using so far the relation less than or equal to, but now we define relation greater than or equal to such that if x is less than or equal to y, then y is greater than or equal to x for all x or y in the surreal numbers. We can also define or prove the following relations. If x is greater than or equal to y and y is greater than or equal to x, then x is equal to y. We're going to call that equal. And then if x, first I'm going to say that sometimes you're going to see a third bar here, third line. So that doesn't mean equal, it means identical because some numbers are going to have different ways of writing them. For example, like in the reals we have 1/2 is 2/4. Well, that's the same, but it's not identical. So that wouldn't justify having a third line. Well, then x greater than or equal to y and not y greater than or equal to x, or well, vice versa. that means x not equal to y. Then we define y different from x. We're gonna read that as different. Y less than or equal to x means y less than x, and the other way around. So to create some more surreal numbers, we just need to use our already existing ones as L or R sets. For example, this is not a surreal number actually because I made a typo, but because this is -1. If we had a 1 here though, that would be a surreal number. We'd have 0 and a bar 1. And you can prove this, you can check if your condition is true, and you'll get that this is would be a surreal number. Not this, because this one has a type, but still, not every form will be a number. Well, like we said, this is going to be 1 and this is going to be -1, and in fact we're going to call some integer bar empty set. This is going to be the smallest integer after n, and empty set bar n is going to be the smallest integer before n. So these two are just special cases where this is 0. What about 1/2 though? For example, fractions, how do we make them? Well, we can make them by creating a sort of midpoint between 0 and 1. So 0 bar 1, let's say. And then we're gonna check that 0 bar 1 plus 0 bar 1 is 1. And although we won't go into arithmetic in this video, you can check this with the definition of addition, and you'll get that this business here is actually 1/2. So the other way around is going to be -1/2 too. Now it gets interesting. The binary tree of surreals is all of this you see right here, but let's break it down. We started constructing these numbers from the empty set. First number we got was 0, so that's why it's at the top. And in the next generation we got 1 and -1. If we continued in this way, we'd have in the next generation not only the expected -2 and 2, but what we know in the real numbers as their inverses, which are 1/2 and -1/2. These are the numbers respectively, but that doesn't really matter. With each generation, we get a new integer and it's negative. So here, for example, 2 and -2, and midpoints between the last generation's integers and the second to last generation's numbers, which all this can be visualized in this tree. Still, you might think this is a greater system than the real, supposedly, but we don't have all the reals. Well, I mean, not in a finite amount of generations, but because that way we're gonna get fractions of the form, say, k, where k is some number, over 2 to the something. I mean, dyadic fractions. Those are called dyadic fractions. So, for example, 2/3. What happens with 2/3? We don't have it. I mean, not in a finite amount of generations, but we do have it. For example, 2/3 itself can be reached by going back and forth an infinite amount of times, first from 0 to 1, and from 1 to 1/2, to 3/4, 5/8. We approximate it by alternating between the fractions that approximate it from below and from above, which is correspondent, in fact, to having a surreal number with infinitely many elements in its L and R. Namely, those would be the fractions that approximate it from below and from above. So what about, say, pi? Well, since we can express any number that's not obtained in finitely many steps, it's a sort of sequence of approximations where infinity the number is reached. Pi can be expressed as the fractions on the left approximating it from below and the ones approximating it from above. So this, for example, would be pi. These ones have to be on the right because no number of L can be no element of L can be greater than or equal to any number of R. That was the definition. I mean, really, this is the way all the reals are expressed, but some are special cases where one or the other or both sets have finitely many elements, like 0, 1, there was 1/2. Alright, now it's going to get even better. So if we can have infinitely many elements in L or R, what's stopping us from making it, I don't know, all sorts of numbers that don't exist in the real? So what about this? We have all natural numbers here, and then the empty set. Well, it can be shown that with finitely many elements in L, we can just consider the biggest. We won't prove it here, but it can be shown. And we said before that n bar the empty set equals, well, this one's gonna be kind of cheating because we don't know arithmetic, but it's going to be equal to n plus 1. And working the quote unquote the same as in the reals. But there's really no biggest number here. You have all integers, and that means this number is not like anything we've seen before. It's called the simplest transfinite ordinal and is denoted by the Greek letter omega, our first infinite number. And so there's also omega plus 1, so omega bar the empty set, or omega minus 133, or 2 omega, or anything else you can think of. So what does omega represent? Well, omega is the simplest transfinite ordinal, or the simplest infinite number. So we really can use it as a starting point for a brand new transfinite binary tree of surreals. We can go to the left or to the right, we can do this to get omega plus 2/3, and we can do this. Look, if we want to get omega through the binary tree, we just have to do this, go to the right each time. And here would be omega. Well, not really. It would be after infinitely many steps, but still. Now, if we wanted to get to omega, we'd have to go infinitely many steps till here, 3 omega till here, and well, what's this? Well, that's epsilon, and it's called infinitesimal. And basically what it means is that we can do this the other way around. By starting with a number with like 0 bar 1, we get 1/2, the new smallest positive number. Then we make the next one, an even smaller positive number, 0 bar 1/2. To make epsilon, we will just use this whole sequence of fractions that approach 0 and never reach it. So, since there's no smallest one. And then we have epsilon equal to 0 bar 1, 1, 2, 1/2, 1/4, 1/8, 1/16, and so on. We're just using the ones that are k over 2 to the n, like the ones that can be reached in finitely many steps, because that's the way we can go. Like this. The binary tree, this will first represent going to 1, and then trying to go back to 0 without actually going back. So we can do this, but we can only go to the left, so we get to 1/2, 1/4, 1/8, 1/16 will be here, and so on. After infinitely many steps, would get to epsilon. And you might think, but how about 0? What if we end up at 0? Well, fortunately, 3 doesn't represent any number twice, so this ensures we don't actually end up at 0. Alright, thanks for watching. I think this topic is really interesting, and if you want some further reading, I can link to some sources in the description. Just leave a comment below asking me for them. Thank you.